So today what I want to tell you about is what we at SeerAI have been building. It's a platform for spatiotemporal data fusion that we call Geodesic. I think it's a pretty new and interesting way to look at data, and I hope you all agree. So first off, who is SeerAI? Well, the three of us, myself, Daniel, Jeremy, and Rob Fletcher, founded SeerAI in 2020. We came from very different backgrounds, but shared a common vision for what we felt was missing within the geospatial data community and beyond even the geospatial and spatiotemporal data, and decided it was high time to build a tool set that we wished existed throughout our careers to tackle some of these problems. So what is geodesic? Obviously, that's the main point of this presentation, is to go into a lot more detail about this. But what I really want to emphasize is this in a nutshell. Geodesic is the world's first decentralized platform optimized for spatial, planetary scale spatiotemporal analytics. Some of us, Rob and I at SeerAI, are physics nerds, so a lot of the naming and iconography is derived from that. Geodesic is a cloud-native platform. It's designed to scale. Really, we wanted to build a platform that was able to solve planetary scale problems, large amounts of imagery, think terabytes or petabytes of data, and bringing it together to solve really complex problems. Spatiotemporal data is very challenging. So the combination of these three things, cloud native, decentralization, and working with heterogeneous data was key for building this. The scale is difficult for a lot of organizations to achieve on their own. Either there's spot solutions or a centralized model where all of the data has to be brought to a singular location in order to take advantage of it. In our case, we try to be decentralized as much as possible. There are times where we bring our own data to our own data stores and our own databases and work with it there, but we don't have to, and that's a key feature of our platform. Just a couple of case studies, some things that we've done in the past. Working with predictive vegetation health. That's actually an example I'm going to walk through in a little bit more detail in this talk. You can see a kind of a presentation and static dashboard at these links for both of these situations. So Geodesic itself is made up of three primary components. Our microservices-based architecture is built of entanglement, spacetime, and Tesseract. And then we have an enabling technology that also interacts with all of these that we call boson. Entanglement basically allows us to capture and encode complex graphical relationships and has an extensible logical ontology. So entanglement is a version-controlled graph database that is built on top of a cloud-native graph database, underneath it. And unlike traditional graph analytics and link analysis software, entanglement's primary mission is to encode use cases, specifically how data fits together to answer questions, even those you didn't know that you could ask. Entanglement is really our gateway to structured knowledge. Spacetime is a spatiotemporal data store. Basically, spacetime allows you to search for data at any place or time on the Earth. Unlike a lot of other geospatial services like this, we focused on making it easy to deal with heterogeneous data. We've adopted the Spatiotemporal Asset Catalog spec. It's an open specification that has been developed by a number of organizations led by the Radiant Earth Foundation to enable the storage and retrieval of virtually any spatiotemporal data source. We lean heavily on that standard, and it's very important for the operation of our platform. We treat all the data within spacetime as a decentralized asset, meaning that no single organization or entity has specific authority over the data that we can enrich and expose. I'll go into a little bit more detail about how spacetime plays with entanglement later. The next one I want to talk about is Tesseract. So Tesseract is for scaling up. So especially when geospatial and spatiotemporal AI models or when you're working with geospatial and spatiotemporal AI models, it's really challenging to get the data in the right form and the right structure for these models. Tesseract is able to prepare data in ways that dramatically simplify the process. So rather than spending 95% of your time on data ETL, restructuring, reformatting, Tesseract makes a lot of the spatiotemporal side of that significantly simpler and scalable up to hundreds and hundreds of machines. Tesseract runs on a directed acyclic graph. It's really optimized for data fusion. So all of the data sets that Tesseract combines can be brought together to extract their combined predictive power. Because we work with a directed acyclic graph workflow, we're able to do virtually any computation as long as you can write the code for the intermediate steps. And then all of the kind of data wrangling steps are code-free. And then lastly, Boson. So Boson is a geospatial service mesh. The intent of Boson is to abstract away a lot of the difficulties when talking between multiple geospatial data services. There's a lot of competing standards for that. We, instead of trying to pick just one, internally we adopt our own for the sake of interoperability between our services. But then Boson allows us to talk to virtually any geospatial backend. So that includes disparate API and data sources, including data that's just at rest within cloud storage, APIs such as Google Earth Engine or the Microsoft Planetary computer, spatiotemporal asset catalog APIs that are hosted by external parties, such as the USGS. Boson allows us to kind of hook into these sources and work with it within our platform as if it were just any other data set. So that's Geodesic. Now I want to go into a workflow using Geodesic from top to bottom, starting with entanglement. Within SeerAI, everything starts with a question. And in our case, there could be many questions that we want to answer. These are just some of the high-level questions that might come to mind where spatiotemporal data and data fusion is critical for finding the answers. We're not focused on any single vertical. We work across multiple verticals. I'm going to focus on an agriculture example today and talk about how that ties into some of the rest of these questions a little bit later. So if we start with a question, how can I monitor the health of a corn crop? What I might do within our platform is just do a text query, a free text search for corn and crop. That would bring back a node representing corn, corn as an abstract concept, but it has more concrete properties and things that we actually care about. So if we're trying to look at monitoring the health of corn crop, the nearest neighbor to this node corn is vegetation health. Now, there's a lot of different ways to measure vegetation health using remote sensing data, but we're going to look at, or I just have a couple here listed for sake of brevity. The normalized difference vegetation index, or NDVI, is the primary one that we'll be concerned about. You'll also notice that even though EVI and NDVI nodes are not directly connected to corn, it's easy to traverse the graph to get to things that might not be directly related to your original question. We think that structuring data within a knowledge graph makes it really simple to get answers to your questions. And even if you are a remote sensing expert, it might be difficult to get your head around some of the knowledge, and entanglement helps you get there a little bit more quickly. So focusing on NDVI, we can look at some of the data sets within the catalog that allow you to measure that. In this case, Sentinel-2, Landsat, and MODIS allow you to observe NDVI. Each of these data sets can be provided by a different host. In our case, because MODIS is a fairly small data set, we've chosen to host that internally for more efficiency. But for some of the other sources, like the petabyte scale Landsat catalog, or similarly, I think it's even multiple petabytes with Sentinel, those can be stored in exterior locations and accessed through the platform as if they were our own data set. So there are a few different possibilities that I want to go through. And the first one here is the possibility is we've queried the graph and there's already a solution. The answer to our question exists as either a model or a data set. So expanding this graph would find a model that was built by SeerAI to predict the NDVI values for corn or other crops, and we could just directly use the output of the data set that we would run. That's kind of the first step that you do in the process. In this case, the model is a node in the graph that is able to estimate various values. So the model itself estimates vegetation health. This data set here, data set weekly NDVI prediction 500 meters, is predicted by that model. You can see as we build up larger relationships between all of these, we have a lot more context when using this model. So maybe that's not enough. Maybe the model that already exists in there at 500 meters isn't enough, and really I need to predict at, say, 30 meters, 10 meters, or even higher resolution using drone imagery. In this case, I'm not able to use this off-the-shelf model. So no longer does a solution exist, but a recipe exists. And so what I can do here is look at other data sets within the catalog capable of observing NDVI. In this case, Sentinel-2 is a data set that most of it is at 10-meter resolution, and that might be more sufficient for the problem I might be trying to solve. So I can use this graph as a starting point, as a recipe for building a new model, but I don't have to start from scratch. I already have all the information that tells me what needs to go into this model. There's also the possibility that I bring proprietary data to the table, something such as fertilization data at the field level, or seed type, or watering schedules. Ideally, we'd like to use this information, but as of today, SeerAI does not have this information. And as a more advanced user of this platform, I might have my own data sets that I know will add predictive power to the model. So I can start with the recipe that's exposed through our graph, and using entanglement, I can connect these data sets and get a more complete recipe that's more suited for the problem that I'm trying to solve. So in this case, I'm going to derive my NDVI prediction model from Sentinel-2, but I'm also going to derive it from my proprietary data sets, my fertilization, seed type, and watering schedule. And that action is actually performed using Boson. So Boson, acting as a geospatial service mesh, is able to reach out to these sources. So either they could be exposed through some web service, the data could be dropped in an S3 or Google Cloud Storage bucket, or other places. Boson is able to reach out to these remote data sources, even non-standard APIs, and transform them into standard geospatial services, such as Stack, OGC Web Services, Esri Geo Services, etc. And this allows us to utilize data from virtually any source. Once a Boson dataset is added into our knowledge graph, and those can be kept separate, those don't have to be exposed to every user of our platform, we can use it with the full wealth of knowledge that exists in entanglement. And basically, we're able to use these data sets as if they were part of our other services, and that allows us to run planetary scale AI models using Tesseract, or explore the data using the space-time service. Once you have all of the data that you care about within the platform, you can explore it and work with it essentially on your own terms. We have a REST API that exposes all of our services, so you can use whatever client you like, starting with the Open API specification for our services. But we've also written a Python API that makes it simple to integrate our services with common open data science Python libraries, such as NumPy, Pandas, Xarray, ZAR, and even deep learning libraries such as PyTorch or TensorFlow. Even our graphs themselves are exportable as network X graphs. So as long as your graph is small enough to export and work with in Python land, you can export it as a network X graph and run any graph algorithms there, or even things like graph neural networks using like PyTorch geometric or libraries like that. All of this is hosted in our hosted Jupyter Hub environment. So users are able to use the pre-configured API, connect to our system, and install any additional libraries that are needed for the specific analysis. The actual analytics, once they're ready to go, we won't go into all the detail about how to deploy these to Tesseract, that Tesseract would allow us to scale up from there. So basically, we can start with our use case, our knowledge graph that represents the what we're trying to solve. These are the data sets that we care about in this case to explore. And I can then use the Python API to list these data sets and explore them, along with some additional metadata and information about the usage and statistics on the data source. Once I have access to these data sets, I can explore what's available, or I can just work with it with my favorite Python tools. Basically, for example, here, when I do a query, I'm doing a query with specific cloud cover properties on this data set in a specific time range, a specific bounding box on the Earth. It brings back a couple of different features, and then I'm able to work with them with whatever tools are my preferred method. This data set would be exportable as, say, a GeoPandas data frame, or just a regular Pandas data frame, an OGR or /GDAL layer. Basically, we're not trying to be prescriptive over how to use our platform to do your analysis. We're just trying to remove a lot of the burden of working with this data and add the ability to scale it up much farther than you could do just in a local notebook, but without as much specific knowledge that might be required to use a system like Dask to scale it up. So here's an example of using Tesseract. So those same data sets, and actually an additional one, I'm exporting basically samples of data. So I'm exporting the normalized difference vegetation index from Sentinel-2. I'm exporting elevation, and I'm exporting nighttime light levels at a monthly level from a data source called VIIRS. Now, all of these data sets are resampled and geo-registered to the same bounding box, same pixel size and everything. The VIIRS one on the right, the pixels look a little bit large, but that's because I'm working at the native resolution of the sensor. I could also do resampling, like bilinear or other resampling, to actually get these on the same, kind of make them look the same. But the pixel grid is identical, so they could be stacked and combined for data fusion algorithms. The example below shows combining all of this data with in Tesseract. What I'm doing is I'm extracting a nighttime lights time series over the entire country of Peru at a fairly high resolution, and then looking at how that correlates with the electricity generated. In this case, this is an external data set I brought in, and you can see a big drop off in the generated electricity right around when the coronavirus pandemic started, and then a ramp up after that. But you can see the kind of the correlation between the electricity generated and the nighttime lights levels. Tesseract is really meant for working with large data. So once a use case is translated into a graph, it can be converted into a much larger job description to specify the work, such as in this case, maybe I want to export a large training set that I want to use for predictive NDVI. In the case of the model that we've called out, I have Sentinel-2, soil moisture, elevation. And then once we have that planned out, we know how we want to work with data, we can run machine learning and deep learning models at very large scale. This is all built to scale up to countrywide problems or even worldwide problems by breaking the task into a lot of small pieces. And there's some pretty heavy machinery behind it that distributes this so we can scale it across hundreds of machines, including GPU machines when deep learning or other GPU heavy activities are needed. Lastly, once we've actually produced some results, Boson allows us to expose it as common services. So in this case, what I could do is expose the results from running our predictive NDVI model as a feature service in like an Esri ArcGIS dashboard or story map. I could expose that as ODSC web services, or if I have some proprietary API that I'm using internally, as long as I've implemented that data service provider within Boson, I'm able to basically expose the data however I want, as long as it fits generally within the standard realm of geospatial data services. So back to this knowledge graph here. So we've done some work. We found that we didn't have everything that we needed. So we expanded this knowledge graph using Sentinel-2 and maybe added in some of my own proprietary data. But this really gets us to the answer to this question. So if I want to monitor the health of a corn crop, I can reference this graph, any models that I've built that I've connected to it, or other information. And this tells me, kind of what is needed to perform this action. Obviously, there's work to be done. The modeling hasn't been completed, but using just standard data science tools and the wealth of tools that you can bring to the table, we can take that even further. But the question that I asked here is just in a single vertical. So this is in agriculture. Maybe that's what I'm working on, but perhaps a colleague or someone else that is working on a problem, let's say in biofuels, ethanol production, which would definitely care about corn production. So imagine that your colleague is asking the question, well, why is my corn shipment so delayed? Well, that's potentially tied to the health of the corn crop. Maybe there's a shortage, there was crop loss, and the corn has to come from a different location. And in that case, these two graphs are related. And without going into all the details about, these are really just toy graphs. These are not all of the detail that could go into these larger use cases, but these could be connected to each other. In this case, now I'm crossing different verticals rather than just focusing on a single vertical. I can now expand this knowledge graph to answer larger questions, supply chain questions, questions that span agriculture, environmental monitoring. I can maybe look at the environmental impact of these ethanol facilities, and so on. Going back to these questions, I can use the geodesic platform, specifically in this case the entanglement knowledge graph, to respond to these other questions that span multiple verticals. So one day, Geodesic might be able to tackle nearly any question, and through judicious use of AI internally, we can unlock even more power. Imagine a system that's constantly growing its knowledge, specifically to help you answer some of your toughest questions. So, of course, to accomplish this, we rely on powerful software underneath, some of it that we've written. But now I want to talk about what SeerAI does with the Packetderm data science data versioning platform. Sorry, I don't have the best words on that one. But we use Packetderm internally to solve a few different challenges. So the three main use cases that we do for Packetderm, and I'll go into what Packetderm is in a little bit more detail if you're not familiar with it in just a second. But we use Packetderm for scalable data ingest and ETL. We use it for machine learning job management, so scheduling, running, and the interaction between multiple machine learning jobs. And then we can also use it for data product management or maintenance. So basically, we can create a version, a data versioned instance of a data product and understand how various changes to the input, modeling, code influence the output. So Packetderm itself is a cloud native and very scalable data platform. Basically, you can create pipelines and repos. The repos store versioned data, and the pipelines run the actual processing so that we can so we can create kind of different flows that run data into the machine learning models and other data science workflows. So with Pacoderm, we work with a few of our microservices. So I already told you about Spacetime and Tesseract. Black Hole is our ETL framework, and it's built on top of Pacoderm. So some of the actual managing of these pipelines we do with our service that allows data to flow in from all these external points. Instead of building our platform on another system such as Airflow for our data ingest, we chose Pachyderm because of its scale, cloud native deployment, full data lineage tracking, and then its lightly opinionated patterns for repos and pipelines. It just fit really well with what we were doing. So Black Hole is able to receive and ingest data from a variety of sources, dumping raw, unstructured data into our messaging system. But raw and unstructured data, while you can throw that somewhere and work with it in a kind of a data lake construct, oftentimes it's better to do some sort of transformation to it so that it's more readily usable. Since our system strongly centers around the stack spatiotemporal asset catalog specification, we do a lot of formatting and processing of some of this data so that it is readily queryable through spacetime. So for that, we use a Pachyderm construct called a spout or a cron. There are two different types of pipelines. Basically, a spout is for processing streaming data, and a cron is for running scheduled tasks. So we can use either of those to read from our distributed messaging system to process data from disparate external sources. We also build crons to directly reach out that doesn't touch our messaging system, so that we can hit other APIs and ingest data that we want to have internally. When we don't want to rely on Boson to connect to external services, we bring data in through Pacoderm, and Pacoderm writes it into spacetime. Now, the loop is broken a little bit here, because if data is leaving Pacoderm to another system, it's no longer directly versioned in Pacoderm. But Pacoderm actually works pretty nicely with spacetime, and we're interested in what future integration looks like as well, like how we can actually maintain this data lineage, as it is pretty critical. So once data is in spacetime, we can query it with using one of our APIs, such as a stack query. Spacetime will return a stack response, basically a list of the geospatial assets that I'm interested in. And at this point, the stack response we have augmented with Pacoderm-based version information. So the Pacoderm commit info that's in the stack response tells us actually the source, location, and all of that within Pacoderm, leading us back to the pipeline that created it, and then all the way back to the code that was run within that pipeline. So even though we're querying data outside of the Pacoderm system, we're still able to trace it back because the ingest is fully managed through the Pacoderm pipelines. Pacoderm also allows us to do machine learning job management. So rather than do everything within our own framework, Pacoderm makes it really, really easy to do these workflows where we have some input repo that contains maybe job configurations, data sources, and other information. And then we can use that to spawn Tesseract jobs, and we can scale them independently, let Pacoderm do what it's good at, and then Tesseract does what it's good at, which is scaling to hundreds of machines for these deep learning jobs and preparing geospatial data and all of that. So in this case, I might have a repo of jobs that I want to have scheduled. So I might build a cron pipeline that points to all of these Tesseract jobs that I want to run. Those would go into a Tesseract pipeline that would be managed by Pacoderm, which would do some initial processing and submit a job off to Tesseract. Tesseract would spin up a large worker pool, and from that large worker pool, it would process data in parallel and write out those results. Once I have those results, Tesseract can trigger webhooks to a Pacoderm service. So rather than a cron scheduling things, I could actually have a webhook from Tesseract kick off even more Pacoderm jobs. There might be some jobs that make a lot more sense to do using Pacoderm flows, or perhaps you have your own instance of Pacoderm that you're running, and you want Tesseract to reach out to that instead of something else. And basically, because the systems are loosely coupled yet still play well together, you can build these extremely complex workflows, including jobs that maybe Tesseract isn't so well suited for. It might kick off some other job that you might want to use a completely different system. And maybe you have a large amount of other data within Databricks, for example, and you need to kick off something there. Pacoderm is a really great glue to link all of these systems together, and we've really focused on trying to do what we're good at and let Pacoderm do what it's good at. The last thing I wanted to talk about is something that we're actively investigating. I'm not very far on it, but I think it's a really interesting concept that I wanted to bring up to the community. So there's a data format called ZAR, and we heavily use it internally. ZAR is essentially a multi-dimensional chunked array format. It's commonly used within the Pangeo community, as well as the Microsoft Planetary computer, as a cloud-native way to store large tensor data, such as what's needed for deep learning. And we can also use this to store the results of running models or large-scale Tesseract jobs. Because it's chunked and distributed, we can put it in virtually any storage system that allows us to write binary blobs. That includes Pacoderm. It's commonly used with S3 or Google Cloud Storage, but I want to talk about a cool application of when you store this data directly within Packetderm. So let's say you have a multidimensional array, something like this. Maybe time runs along this dimension here, and then the space represents the grid. Every block within that in a SAR data set is stored as a separate chunk, and those chunks are compressed and distributed across some sort of object store that could be a file system, S3, Google Cloud Storage, Redis, database. It really doesn't matter. SAR, the Python library for SAR has a lot of these stores implemented. We have some of our own that we work with internally with another language that we've built that is able to work directly with SAR. But these individual chunks are referenced by basically their chunk index. And because Pachyderm is really good at versioning individual pieces of data, rather than throwing one big massive file in there, we can let Packetderm manage these individual chunks. So rather than writing to S3 or Google Cloud Storage, what I could do is write directly into a Packetderm repository, and then these individual chunks and the metadata associated with this array can be versioned in that case. So in this case, time index 5, row 1 and column 2 represents this chunk, and so on for the others. And then the colors might represent something that I care about monitoring large scale. So perhaps I have a deep learning model used for land cover or extracting road surfaces or something like that. That data set could be huge. If I have a land cover map for the entire US at 1 meter or road surface map for the US at 1 meter, that's going to amount to a lot of data. And every time something changes, I don't want to rebuild that whole data set or store separate version information for all these changes. When I write it into a Packetderm repo, I actually would have that natively. I'd have each of these chunk versions, actual managed in just a repo. And then using Packetderm's S3 gateway, I could actually access all of these as if they were just in an S3 repo, an S3 bucket instead of it looking like a Packetderm repo. So that way I could actually use it externally with other tools that are compatible with S3. So if I store this in a Packetderm repo, then Packetderm stores the version. So I can see like maybe a couple of these chunks have changed, and now I don't have to store the entire thing. I just have to store what's changed. And because we maintain lineage on these data sets, we can trace the output back to models, back to model inputs, and back to the code that generated them, because we have full lineage and all the data that we store in there, all thanks to Packetderm. So that's what I wanted to talk to you about today. I'm happy to take any questions that you might have about the platform, future plans, or anything else. I also wanted to point out we're currently talking to clients about early adopters and beta users. Right now, the platform is something that we use internally to build our data products. But if you are interested, reach out to us and let us know.